You know that feeling, right? You're trying to get your head around some big tech system, maybe Kubernetes, and it's just information overload.
Oh, yeah. Acronyms everywhere, diagrams that look like spaghetti.
Exactly. And you just wish someone would give you the shortcut, like what really matters, what's actually happening.
Well, hopefully that's what we can do today. Give you that shortcut for a really fundamental piece of modern tech.
Okay, great. So what's the focus for this deep dive?
We're diving into Kubernetes. It's that huge open source platform pretty much everyone uses for containerized apps now. But we're zooming in.
Right, because the control plane gets a lot of attention, the big brain making decisions,
It does, but the actual work, the heavy lifting, that happens down on the individual machines, the nodes.
the workhorses. So our mission today is to unpack the, what, 3 critical components running on every single node?
That's it. The kubelet, Kube-Proxy, and the container runtime. Often overlooked, but honestly, if you want to understand how Kubernetes actually works at the ground level,
You need to understand these guys.
absolutely, they're how high-level instructions become, running applications.
So the promise is, by the end of this, you, our listener, will have a really clear, hopefully beginner-friendly picture of how these components work together, how containers run, how they talk to each other, how they follow the plan.
Yep. You'll see exactly how these nodes do the work.
Okay, but before we jump into the deep end, maybe we should level set on a few key terms, just quickly.
Good idea. So first up, cluster. That's just the whole set of machines Kubernetes manages.
And those machines are the nodes
Exactly. Physical servers, virtual machines, whatever. That's where your apps run.
inside pods, right, which hold the actual containers.
Perfect. Pods are the smallest thing you deploy. Usually one main container, maybe some helpers.
And overseeing all of this is the control plane.
Right, the management layer, the API server, the scheduler. That's the brain.
And we talk to that brain using Kubelet.
Usually, yeah. That's the command line tool for interacting with the cluster via the API server.
Okay, basics covered, so let's set the stage. Nodes are the worker machines. Can you maybe expand on that a bit? What makes a machine a node?
Sure. So think of a node simply as a server that Kubernetes can use. Could be bare metal in your own data center, could be a EC2 instance in AWS, a VM anywhere, really.
Gotcha.
Its job is to provide the CPU, the memory, the network resources to actually run your application workloads. And like we said, it hosts those pods.
But these nodes aren't just doing their own thing. You mentioned the control plane manages them. How does that work? How do they know what pods to run?
Ah, yeah, that's key. They're definitely not independent. The control plane is constantly making decisions like, okay, this new web server pod needs to run somewhere. Node 3 looks good.
And it sends instructions down.
Exactly. It sends instructions down, usually via the API server, and it monitors the health of the nodes and the pods running on them.
And this is where our trio comes in. The kubelet, Kube-Proxy, and container runtime. They're the bits on the node that actually listen to the control plane.
Precisely. They are the essential agents running on the node that receive those instructions, execute them, manage the networking, and report status back up. They make the node a functioning part of the cluster.
Okay, so let's give a quick preview of each. The kubelet is like the node's manager.
Yeah, the node's agent maybe,
Yeah.
constantly talking to the control plane, making sure the pods it's responsible for are running correctly.
And Kube-Proxy, networking guru.
Totally. Handles all the network rules, makes sure pods can find each other, talk to services, reach the outside world. It's the traffic cop.
And the container runtime, that's the engine room.
That's a good way to put it. It's the software that actually does the low-level work of starting, stopping, managing the containers themselves.
Like Docker, container.
Exactly those things. We'll get into the specifics. But together, these three are why a node can actually do anything useful in Kubernetes.
Okay, that sets the stage nicely. Let's dive deeper into the first two, which you kind of framed as the brain and the brawn of the node. Kubelet and the container runtime. Let's start with Kubelet, the agent. What's its core job?
So, the kubelet. It runs on every single node, and fundamentally it acts as the bridge between the control plane and the node itself, its main goal. Making sure the containers specified for its node are actually running and healthy.
Okay, running and healthy.
Yeah.
That sounds simple, but I imagine in a dynamic cluster that's pretty complex.
Oh, it absolutely is. Think about what that involves. First, it has to constantly talk to the API server, which is part of the control plane, right? To get the latest pod specifications, basically, the blueprints for what should be running on this node. Run this container image, give it this much memory, open this port, stuff like that.
Okay, so it gets the orders, then what?
Then it has to manage the life cycle of those pods. It tells the container runtime, okay, start this container, or this one needs to be stopped, or crucially, this one crashed, restart it.
The self-healing aspect.
Exactly. And while it's doing that, it's also constantly monitoring, checking the health of the pods, using things called probes, like knocking on the door to see if the app inside is okay.
Liveness and readiness probes.
Yep, those are the ones. And it's also monitoring the node's own health CPU usage, memory pressure. All that status gets reported back up to the control plane.
Why report node health back?
So the control plane knows if a node is struggling. If a node is unhealthy, the control plane might decide to stop scheduling new pods there or even move existing pods off it.
Makes sense. So key features are pod management, health checks, node reporting.
You got it. A concrete example. Control plane says schedule pod X with a web server onto node A. The kubelet on node A sees that, tells the container runtime to start the web server container. If that container suddenly crashes,
The kubelet jumps in and restarts it.
right, often automatically, without you even needing to intervene. It tries to maintain that desired state defined in the pod spec.
Okay, so kubelet is the manager, the supervisor. Now, the muscle, the container runtime. You said kubelet tells it what to do.
Exactly. The container runtime is the software that does the actual low-level heavy lifting of running the containers. It interacts with the OS kernel to create the isolated environment, pull the image, start the process, stop it, delete it.
So kubelet says jump. Container runtime says how high, using container tech.
Pretty much, yeah. Its key functions are executing containers based on kubelet's instructions, pulling the necessary container images from registries like Docker Hub or others,
Okay.
and managing those fundamental container operations. Start, stop, delete.
You mentioned Docker earlier, but also container, CRI. Why multiple options? Isn't that complicated?
It could be, but Kubernetes has something really clever called the CRI, the Container Runtime Interface.
CRI. I've heard of that.
Yeah, it's basically a standard specification, like an API. Before CRI, Kubelet kind of had specific code for, say, Docker, which wasn't great for flexibility.
Tied you to one runtime.
Exactly. CRI creates this abstraction layer. As long as a container runtime implements the CRI standard, Kubelet can talk to it.
Oh, nice. So you can swap them out, use Docker or containered or CRIO, and kubelet doesn't really care as long as they speak CRI.
Precisely. It makes the ecosystem much more flexible and robust. It focuses on compatibility through this standard and allows runtimes to focus on efficiency, being lightweight and fast.
So when kubelet gets that spec for the web server pod,
It doesn't start the container itself. It turns to the container runtime, whichever one is installed and configured, and says via the CRI, hey, pull the Nginx image and start a container using it with these parameters, and the runtime does the actual work.
got it. So they're tightly integrated. Kubelet is delegating the doing to the runtime via this standard interface, while kubelet keeps monitoring.
Perfect summary. A clean separation of concerns, high-level management versus low-level execution.
Okay, so we've got containers running thanks to kubelet and the runtime. But isolated containers aren't much use. They need to talk to each other, right? And to the outside world.
Absolutely. And that's where our third musketeer comes in,
A
Kube-Proxy.
network navigator. What's its primary mission?
Kube-Proxy runs on every node too, and its entire focus is networking for pods. It ensures network connectivity works correctly, pod-to-pod communication, pod-to-service communication, external traffic coming into services. Kube-Proxy manages the rules for all of that.
It sounds like a network admin built into every node. What are the tricky parts it handles? Because Kubernetes networking can seem like magic sometimes.
It really can. One of the biggest challenges Kube-Proxy solves is that pod IPs are ephemeral. A pod might crash, get restarted, and come back with a completely new IP address.
Right, you can't rely on pod IPs directly.
Exactly. So Kube-Proxy maintains network rules on the node itself, often using underlying Linux tech like iptables or IPVS. These rules act like a virtual router or load balancer for the pods on that node.
Iptables, IPVS, those are Linux things.
Yeah, they're different kernel features for manipulating network packets. Kube-Proxy basically programs these tools based on information it gets from the control plane about services and endpoints.
Okay, so services are key here.
Absolutely critical. A Kubernetes service provides a stable IP address and DNS name for a set of pods. When you send traffic to a service, Kube-Proxy intercepts that traffic. on the node where the request originates or lands, and routes it to one of the actual healthy pods backing that service.
Ah, so it does the translation from the stable service IP to the changing pod IP.
Yes, that's the core of service discovery. It maps the abstract service to the concrete, potentially shifting pods, and it usually does load balancing too, if your service has 3 replica pods.
Kube-Proxy spreads the traffic across it.
Exactly. It distributes the requests, usually in a round-robin or random way, so no single pod gets overloaded. It makes your application scalable and resilient.
So key features: service discovery, load balancing, and it uses different modes like IPTables or IPVS under the hood.
You've got it. So if you have that web app service running on 3 pods, Kube-Proxy on every node knows how to find those pods and distribute client requests across them, even if pods get replaced or rescheduled. It makes the network just work.
Okay, this is where it all comes together. We've met the Kubelet manager, the container runtime engine, and Kube-Proxy navigator. How do they actually orchestrate? Let's walk through that pod creation scenario again, but focus on the interplay.
Great idea. So, step 1. The control plane decides to schedule a new pod onto Node A. It writes that pod specification to the API server.
Okay.
Step 2. The kubelet on Node A is constantly watching the API server. It sees this new pod assigned to it. It reads the spec, what image to use, ports, etc.
Right.
Step 3. The kubelet doesn't start the container itself. It talks to the container runtime via CRI. Hey, runtime, pull this image and start a container based on this spec.
And the runtime does the heavy lifting, pulls the image, starts the container process.
Precisely.
Yeah.
Step 4. While this is happening, or maybe slightly before or after, depending on timing, the Kube-Proxy on Node A, and potentially other nodes too, gets updated information from the control plane about this new pod potentially belonging to a service.
Ah, so it knows where to send traffic to this new pod if needed.
Exactly. Kube-Proxy updates its local network rules, IPTables, IPVS, whatever mode it's in, so that traffic heading for the relevant service can now potentially be directed to this brand new pod.
So the pod starts, and networking is ready for it almost immediately.
That's the goal. And then ongoing.
The kubelet takes over monitoring.
Yep. Kubelet continuously checks if the container is running, if it's healthy, using those probes. It reports the status back to the API server. Pod is running, pod failed, probe successful, etc.
And Kube-Proxy just keeps those network rules up to date as pods come and go or services change.
Constantly. Both Kubelet and Kube-Proxy are in this perpetual loop of watching the API server for changes and ensuring the node state matches the cluster's desired state. Kubelet for pod lifecycles, Kube-Proxy for network routing.
It really drives home why you need all three. You can't just have one.
No way. The kubelet is the manager, the enforcer of the desired state for pods. The container runtime is the indispensable engine doing the low-level container work. And Kube-Proxy is the network magician making everything reachable and scalable.
Take one away, and the whole thing falls apart.
Pretty much. You'd have containers that can't start or can't be managed or can't talk to anything.
So the big picture is that these three components, working together on every single node, are what allow Kubernetes to actually execute on the promises of the control plane. They turn abstract definitions into running, networked, managed applications.
That's the core insight, definitely. It's this incredible synergy between them, this constant communication and coordination, mostly invisible until something breaks.
Right. It's not just separate parts. It's how they interact constantly.
Exactly. That's what gives nodes their power and makes the whole Kubernetes system work.
So hopefully this deep dive has given you, the listener, that foundational piece. You now know how your containerized applications actually spring to life, how they stay running, and how they connect within a cluster. You could look past the abstractions a bit.
Yeah, you have the vocabulary and the concepts to understand what's happening under the hood on those worker nodes.
Okay, to wrap up, let's leave you with something to think about.
Now that you know about this sort of invisible dance between the Kubelet, Kube-Proxy, and the container runtime, what new questions pop into your head? Maybe think about resilience. What happens if one of these components starts acting up, maybe subtly misbehaving? How would that impact your application, and how might you even start to figure out which piece is the problem?
That's a good one. Because often you just see the pod failing, right? Not why it's failing at the node level.
Exactly, something to ponder.